What do we do when and if we discover alien life? In one instance, we already know because it happened, and then it didn't. In 1996, none other than then President of the United States, Bill Clinton, announced on the south lawn of the White House that evidence for microbial life on Mars had been found in the Allen Hills 84001 meteorite, in the form of what appeared to be microscopic fossilized evidence. For a short time, the public believed that alien life had been found. Then the results were called into question by other scientists, and to this day it's not settled as to whether that and other meteorites of Martian origin carry evidence of past life on that world. What was interesting was the public reaction. Everyone just seemed to say, well, there it is, and moved on. We often think that the discovery of life on other worlds would be a titanic game changer for humanity, but for much of the late 19th and early 20th centuries, it was a household belief that Mars was inhabited by little green men building canals. This was even erroneously backed by some of the scientists of the time, such as Schiaparelli and Percival Lowell. Only when Orson Welles scared the daylights out of some with his broadcast of his version of H.G. Wells's War of the Worlds did Martian life become a public problem. But even then, not as many reacted badly as is often portrayed. But what of an advanced alien civilization? What if we spotted a technosignature, say a giant Dyson swarm, built by someone so powerful that our technology seemed like sticks and stones in comparison? What if it were a machine civilization, so divorced in experience from our biological reality that it's difficult to even comprehend it? Would society react the same way, or would it be Orson Welles all over, only this time it's real?
You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Duncan Forgan. Duncan was a postdoctoral research fellow at the School of Physics and Astronomy of the University of St Andrews. His research focused on numerical simulations of protoplanetary disks. He is especially noted for his research into numerical astrobiology. He has appeared in the BBC's Stargazing Live, The Sky at Night, and Horizon.
Welcome everyone to Event Horizon with me, John Michael Godier. If you enjoy what you hear, fall into the Event Horizon, hit the like button, and become an active subscriber by ringing the bell. Duncan Forgan, welcome to the program.
Hi, it's great to be here.
Now, Doctor, correct me if I'm wrong, your early work was on planetary formation, a sort of a different model than the standard model that's out there. Can you explain that?
Yeah, sure. So my PhD work was on, as you described it, an alternative model of planet formation. So the kind of accepted model, the model that explains the most about what we see in exoplanetary systems, basically requires you to start with a star. And when you build a star, one of the things you get as a byproduct is a disk of material around that star. And inside that disk, you have lots of gas and lots of dust. And the dust grains inside that disk can collide and stick together and get slightly bigger, and then collision after collision after collision, you slowly start to assemble bigger and bigger things. You go from dust to pebbles to boulders to asteroids and comets, and then all the way up to planets. And that's the kind of bottom-up approach, and that's a very successful theory in explaining quite a lot of what we see. But what we're starting to realize is that there are some planetary systems that don't really fit that picture very well. And we're starting to see evidence of another type of, well, it's planet formation, but it's also low mass star formation. So it's bridging that boundary from when a planet stops being a planet and becomes this intermediate category we call a brown dwarf. And this is a top-down approach. So instead of trying to build your planets from little dust grains upwards, what actually happens is the disk itself is so massive that it can break apart under its own gravity, and these fragments that come out are about the size, well, maybe 3 or 4 times the mass of Jupiter to start with, at the very minimum. Some of them can be much bigger than that still. And the trick then is to figure out what happens next, because this happens very quickly. So in the accepted model of planet formation, it takes you millions of years to get to a Jupiter. In the model that I studied for my PhD and for subsequent research, you can get something that's 5 or 10 times the mass of that in less than 10,000 years. So this is a very rapid way of building quite large objects. And in this alternative theory, it might even be the case that some of these bigger objects will lose some of their material and end up being smaller objects. And if everything lines up and you're a very lucky body, then you might end up forming a solid core, lose your atmosphere, and you might have something that's more like a super Earth or even potentially even an Earth-sized planet at the end. So a lot of my research in that area was to try and figure out, well, A, can we do that? Is this chain of events possible? Can you go from big disk to big clump of gas to small planet? And if you can, how often does that happen? And the work that I did showed that you can do it, but it's not very common. So the chances are that if you're looking at planets that are about the size of the Earth, they're formed by the more accepted model of planet formation.
Is it possible that both models might be correct and that you have situations within the disks that can be different?
So one of the last things that I looked at in recent times, and I have a paper that's sitting in preparation and will hopefully be submitted at some point, is investigating this very idea that the two formation mechanisms could kind of coexist in the same system. And so at the minute it seems quite possible. Whether we expect to see lots of systems doing that, and whether we expect those systems where it's all happening at once to look like what we see out there in the universe or not, is still a bit of an open question. It doesn't look like that's the case. It looks like the planets that we see tend to be planets that are built purely using the accepted model, and that the alternative model is more for building binary star systems with brown dwarfs in them, and yeah, maybe the occasional oddball system that accepted models find it difficult to explain. We have some systems with lots of giant planets at quite large distance, and the kind of the standard theory of planet formation doesn't do very well with those, whereas the alternative theories do quite well. So it could be a case of looking at a system and saying, well, chances are it's either going to be this way or it's going to be that way. And most of the time it's going to be the standard way, but for all your oddballs and your difficult situations and your big systems with lots of stuff, this alternative method is very useful for explaining those.
Now, is it possible to investigate this? Can you look at protoplanetary disks around young stars and determine if this is the case?
Well, excitingly, yes. In the last 5 years, we've really started to open up our understanding of the disks as they're forming, as they're starting to evolve from their young state, which is quite massive compared to the star. So you've got a star being born and the disk around it, and the star and the disk initially are about the same mass. And then that very rapidly changes. The disk flows onto the star very quickly, and the star builds up mass, the disk loses mass. So you have this very short window in which this really unstable, fast, top-down model of building stuff can happen. The problem with it is that this stage is usually when the entire system is enclosed inside a big shell of dust and gas that's still falling into the system. So your usual approach is using, say, visible light, and even sort of the short infrared light find it very hard to penetrate. So you want to go to nice long wavelengths and really peer in. Then the challenge with that is that you peer in at long wavelengths, but you don't have the ability to resolve what's happening. All you can see is kind of blurry images. And it's really since, in the last 5 years, I would say, when we have systems like ALMA, which is a very big interferometer that's working at these longer wavelengths that gives us the real sharp resolution, the clarity to see what's actually happening. And so we can see these disks aren't just disks, they have lots of structure, they have rings, they have spiral arms, they have what looks like warps, and we can see planets being born in these systems. We can see the beginnings of these objects. And it's really the first time we can stress test these theories and say, right, what's really happening here? What's the observational evidence for these theories that we've been cooking up, on paper and in the computer for, the last 15 or 20 years. Now we're really putting them to the test.
That was your original work, but since then you've also moved into astrobiology. What sparked your interest in going in that direction?
Well, it was coeval. I was doing work on planet formation and astrobiology at the same time. As a PhD student in Scotland, we were required to take some courses to kind of fill up the first year of our degree, just to have some taught material as well. And I took some courses on astrobiology, and I actually took a course on SETI as well. It was a bit of a rarity at the time to have a course specifically focusing on SETI. We were quite lucky in that regard. And the subject got me very interested, and clearly it was very relevant to exoplanet science, because if you want to think about life in the universe, you need to start with the habitats. And as far as we can tell, planets are among the best habitats for producing life. At least we live on a planet. It's a good place where you can have stable chemistry. The temperature can stay roughly the same. You can be shielded from all sorts of radiation nasties with the right atmosphere. There's lots of things to recommend a planet as a life hosting object. And then SETI itself, looking for intelligent life, kind of demands you to be even more focused on where life can be. You know, we look at microbes, and we look at extremophiles, which can survive in these really what we would consider very hostile environments: high radiation, high temperature, high salinity, low temperature, low salinity, all these environments where humans would perish in minutes. We have organisms surviving. If we're looking for big animals with big brains, then that really focuses the limits of life to something even narrower. You know, the habitable zone in that sense. The range of temperatures we can survive in is even lower than it would be for one of these crazy organisms. So it really pushes your focus. And during that time, I was thinking about how exoplanet science should affect our understanding of intelligent life, and how we hadn't really figured out how to incorporate our knowledge about exoplanets into the question of how many planets we expect to have intelligent life on. Straight away, I came up with some ideas as to how to work in these ideas in a statistical kind of way, build a model that sort of lets us run an experiment in the computer saying, here's a Milky Way with a population of exoplanets that looks statistically like our Milky Way. If we make some assumptions about how intelligent life appears, what happens, you know, and how does changing our assumptions change the answer, and kind of just exploring the hypothesis, as it were. So that was actually my first paper, which is a bit unusual for somebody in my field to take what is a bit of an oddball subject and have that as their first publication. But it was a really interesting idea, and it got a lot of press interest, and it was my first exposure to, well, doing the press junket, really being in a press release, and then having to, you know, do lots of interviews and speak to people with various ideas about what your work said and what your work meant. And it was very odd. You know, I saw my work being discussed in the editorials of quite big newspapers, and they were putting some weird political spins on it, and it was very, very unsettling. So it was a really big learning curve for me. I learned a lot about what you should say in a paper and what you should say in the newspaper, and how they can sometimes be the same thing and how they can sometimes be separate things. And yeah, it was quite an experience. It was a baptism of fire.
A baptism of fire, but that's the media. You know, the media is not, when reporting on science, they are not always 100% accurate or 100% ethical in some cases.
Well, that's certainly what I discovered.
Yes. But now, astrobiology it used to be considered pretty fringe, but not so much anymore, because I think we're, you know, through the efforts of the SETI programs, which are legitimately looking for signals, and through the efforts of scientists writing papers, it's a little bit more legitimate of a question now to ask, are we alone? But unfortunately, we get into this pop cultural gray area where people talk about the UFO phenomenon and all of that. Do you think there's any possible validity to that?
As regarding UFOs, I haven't seen anything that would make me consider that the evidence was pointing towards something extraterrestrial. I think one of the things that I've discovered in my research of not just the search for intelligent life, but also some work that I've done in the last few years on propulsion and interstellar travel, is that it's really hard. Really hard. And if you're wanting to transport biological material, very hard. If you want to transport walking, talking aliens, really, really hard. And it seems, I mean, you don't want to say impossible, but extremely, extremely unlikely that these accounts that you see of UFOs landing, of people having close contact, close encounters of the third kind, or whatever you want to describe it, there is very little evidence that you can trust these accounts. And that's not to cast any aspersions to people that have these experiences. They're presumably very genuine experiences, and that they wouldn't say these things if they didn't believe them to be true, because they're quite fantastical and weird. And you wouldn't say something like that unless you believed sincerely that this is something that had happened to you. But extraordinary claims require very extraordinary evidence, and in the cold light of day, I've not seen an account that is ironclad to say this is proof that we are not alone in the universe and that there are aliens visiting the Earth. There's nothing that I can point to that says this makes me consider that as a possibility.
I've seen nothing either. You mentioned something interesting. You mentioned that space travel, interstellar space travel, is extremely difficult. Now, could that be a viable solution to the Fermi Paradox, that it's simply just too hard and no one colonizes galaxies because you just have to work with what you have in your own star system? Is that a viable solution?
Okay, so maybe I should quantify that. Interstellar travel with spacecraft above a certain size is very hard. Interstellar travel with spacecraft below a certain size becomes increasingly easy. And now what's worrying about that is that it makes the Fermi Paradox quite strong. So you can imagine a situation where maybe not far in the future of humanity, maybe 100 years, maybe 200 years, we could start launching spacecraft that have enough instructions on board to create copies of themselves. If they travel to another star system and make a copy, then you now have 2 probes. Those 2 travel to another star system, you now have 4 probes. And so exponentially you start to grow this fleet. And some work I did a few years back with a student of mine showed that if you had this kind of approach and you started with a spacecraft that could travel at the speed of Voyager, which is a snail's pace, right? It's 100,000th of the speed of light. It's not fast compared to the speed of light. If you started at that speed and all you did was use the gravitational fields of the stars you visit, so basically doing slingshot maneuvers like Voyager did to get out of the solar system, you could build the speed of those spacecraft up to about 1 to 5% of light speed, which is a lot better, and you'd have loads of them. So you could potentially explore the Milky Way within 10 million years. Now that is a heartbeat compared to the age of the Earth, which is, over 4 billion years. So that really makes you think, okay, if the Earth has been around for such a long time, and there have been many intervals of 10 million years in that time, where a not particularly advanced civilization, who the only things you have to figure out are how to make copies of small things and how to program the computers to navigate autonomously and to be fault tolerant even under high radiation, which these don't seem particularly insurmountable challenges. If you can do that, then within 10 million years, you can have a probe around every star in the Milky Way.
Now, can you maintain that? So through like the von Neumann probe, can you maintain that for indefinitely for millions of years if your probe can repair itself, or does it, to touch on your more recent paper, does it eventually go corrupt and just stop working or do something?
So to look at my more recent work, one of the objections to this is that as you keep on making copies and copies, you're going to introduce errors into the copying because your machines are getting struck by cosmic rays and bits in the computer are getting flipped from 0 to 1, and some of these mutations will be benign, some will destroy the spacecraft and make it inoperable, and some will change its behavior. In the same way that small changes in the DNA and the genes of animals can cause natural selection and it can cause evolution. And the argument is that maybe evolution would then happen in these machines. And the easiest way for a machine to make a copy of itself is to take another machine and take it over and basically salvage it for parts. And this is the same behavior that predators have with prey, right? Predator eats prey, gets protein, builds up its body. In this case, it would be a predator probe, takes prey probe, dismantles it, and uses its pieces to build another copy of itself. It's the same rough function, but there you go. And the argument could be that, well, if this happens, then the predators basically eat all the prey and the number of probes goes down a lot, and therefore that's why you don't see signs of probes, say, in the solar system or in any other star system, because all the probes have been eaten, right? So the predators have eaten all the probes and then the population collapses because it runs out of food supply.
And this would be a natural, well, not natural, and that's in a normal sense, but a natural ending of a colonization using von Neumann probes, right?
Right, so it would mean that the program that you designed into the machines is no longer the program they're following, right? And as a result, you may not have as many probes doing the exploration. They may be going in the wrong direction. If you've got a predator probe and it's looking out and saying, my next target's meant to be there, but I know there's a whole bunch of prey back at that star system I've just visited, I'm going to turn around. These things can kind of stop the exploration process. It can make it take longer, or it can halt it entirely. And so this is one objection to this idea that self-replicating probes can basically explore the whole Milky Way so quickly that we should see tons of them, and we don't. And so one of the solutions is, the reason we don't is because there's lots of predators and they eat the prey, and there's not as many.
That's sort of scary if you think about it, because if we start sending out Breakthrough Starshot or something, we start sending out microprobes and they start disappearing, then there could be something for being a predator against them out there. Now, the other thing about this is that when you begin to start harvesting raw materials of star systems to build these von Neumann probes, Carl Sagan years ago pointed out that you could basically consume a large fraction of the galaxy by sending out a von Neumann probe. So I guess also your concept would explain why that hasn't happened, why, half the galaxy hasn't been converted into von Neumann probes, and it doesn't appear that any fraction of it has been. So I guess it would peripherally also solve that question too, right?
To some degree. I mean, if there was no evolution at all in the program, and every probe visits every star, and you have a sensible end point, which is once everything's been explored, sit still, then you wouldn't have this issue of everything being converted into probes, and that you'd lose all the planets in the Milky Way to this kind of exponential eating process. If something went wrong and there was evolution, but in a negative direction, if that's such a thing, then yes, you could find that maybe the reproduction goes out of control. We have a similar concern about nanotechnology on the Earth, in that if you produce self-replicating nanoprobes that, say, use carbon to make copies of themselves, then if something goes wrong with the programming and they go out of control, then everything that's carbon gets turned into probes, including us, right? And they call this the grey goo scenario, because the entire planet's surface gets turned into grey goo. And again, there are people who are thinking about this carefully, and there are people who have come up with precautions and protection against it. Doesn't guarantee it will never happen, but at least people are thinking about it. So I would assume that if somebody was smart enough to send a von Neumann probe out into the universe, they would have thought about these things carefully too. And in fact, this is actually one of Carl Sagan's favourite objections, is that the dangers of sending probes like this are so high that civilizations would agree not to send them ever again, or at all. So the reason we don't see them is because they're so dangerous that they could convert the entire Milky Way into probes, that no civilization with any sense of moral judgment would do so.
So that, I guess, would involve another solution to the Fermi Paradox, which would be the zoo hypothesis, where they just sit there and wait, watching, no contact, until you start building something like seriously advanced artificial intelligence or a von Neumann probe. And that's when they step in and say, you can't do this. You have to make sure the rest of the galaxy is protected. Now, you could also get into a situation, too, where if you have multiple civilizations in a galaxy, and they're all producing von Neumann probes that are eating each other, then it becomes a sort of like a von Neumann Cold War, essentially.
Yeah, well, this is the thing. And the problem with it is that the minute you launch that probe, because it's quite hard to travel at any decent speed with people on board, you're not really in control. So the conflict will then take place without your orders. And if the conflict lasts a long time, that conflict will trigger arms races in the probes. And we see when we have multiple predators against the same prey in ecosystems on the Earth, we can see how the predators change their strategies to suit themselves, to ensure that they propagate further. So we could have some very unintended consequences of these kinds of actions.
Sounds increasingly dangerous, even more dangerous than I thought the concept might originally be, especially if you start involving advanced artificial intelligence in the probe. Then you have some...
Well, this is the thing.
By doing that, you would make the probe even more complex, meaning that more could go wrong. Again, like you say, the cosmic ray exposure or anything like that can just cause it to become essentially a galactic monster and attacking everything it can for resources. But thankfully, this does not appear to be the case. We see no evidence of this when we look out into the galaxy. Now, what is your gut feeling on the Fermi Paradox? What do you think is the actual solution?
Well, I mean, I've spent a long time thinking about it, and I have a book that's out through Cambridge Press, and it's called Solving Fermi's Paradox. Unfortunately, I don't actually solve Fermi's Paradox in the book. All I really do is list the solutions that I can find and think of, and I came up with, I think, 66 distinct solutions. And they kind of fall into three categories. So they fall into the category of, well, maybe intelligent life is rare. The second category is that maybe intelligent life doesn't last very long. And then the final category is that maybe intelligent life is very hard to see. And into this last category, a lot of interesting stuff and kind of kooky, crackpotty stuff falls in as well. So, this is where the UFOs live, and the men in black, and the ancient astronauts, and all the stuff that is, quite rightly poo-pooed by scientists. So my feeling is that the answer, if there is an answer out there, is probably some mix of the first two. It's probably the case that intelligent life is actually quite difficult, or it's simply rare. It requires a lot of luck. When you think about the various contingent circumstances that have occurred on the Earth to not only produce life, but to produce life that reproduces sexually, that has relatively large bodies, large brains, and then the fact that there was, at some point there were 6 species in the genus Homo, and now there's only 1. Why was it us? What did we do to earn that particular distinction of being the survivors? What were the circumstances that drove humans to continue to dominate their surroundings and to basically cover the entire surface with their population? It may well be the case that, as I think it was Stephen Jay Gould said, that if you rewind the tape and play it back, you'll get a very different answer. And that if you rewind the tape back far enough and play again, humans never really appear as an intelligent species. It's really not clear to me that it's the case that humans were destined in any way to be intelligent. I don't think it's the case that planets that are around for long enough with life make intelligent life. I wouldn't be surprised if we went out there, found planets with life that had been around for, maybe twice as long as the Earth and had showed no signs of even producing, relatively large animal life, let alone intelligent life. So my feeling is that intelligent life is hard, and also it's probably nasty, brutish and short. To quote Thomas Hobbes, we're not very good at looking after the planet. It's pretty obvious we're not. Climate change is a problem. The fact we still have an awful lot of nuclear weapons is a problem. Our research into all kinds of technology with existential risk is a problem. There are lots of possible ways that we could just end ourselves, and it's not clear to me that we possess the wisdom as a species to get past all of them. So if that's true for us, then that might explain why we don't see any signs of intelligent life out there, that they struggle to become intelligent and they struggle to survive.
And on that, we have to take a break. I'm joined today by Dr. Duncan Forgan, author of Solving Fermi's Paradox. We'll be back in a moment.
If you're new to Event Horizon, hit subscribe. It's free, and we upload videos every Thursday, plus additional content.
And we're back with Duncan Forgan. Now, there's another possibility, too, that's related to the idea of rare intelligence. Also, it could be that Earth itself is incredibly rare, and that just the right factors were present for this planet to produce life and intelligence at all. Now, what are some of the factors that contributed to the genesis of life on Earth?
Well, there are lots. There's the fact that we have a planet that has a relatively large amount of surface water. We have an atmosphere that's thick but not too thick. In terms of producing life, some of the things that we need to have is a suitable background in which to do the right chemistry, and essentially one of the things you're needing there is protons and electrons to move in the right direction. You want the right chemicals, you want a good dose of sunlight, not too much, not too little. You want a bit of ultraviolet light, not too much, not too little. And if you mix that all together and wait long enough, then maybe something happens. But the key thing really is stability. You need relatively quiet conditions for life to form. Now, we know that on the Earth, the minute that things settled down, we started to see in the fossil record signs of life. It's not clear that that was going to be the case. We can't use the Earth as a single sample and say that's what always happens, that the minute that life can arise, it does. That's not necessarily true just based on one sample. But it certainly is clear that there are certain parts of the Earth's history where life can't arise. And what we're seeing in the exoplanet systems that we know about is that early part, what we call the Hadrian period, because it was literally hell on Earth, we see hell on other planets and that hell is not going away. We see planets that are basically entirely lava on the surface. We see planets that don't really have a surface. We see giant planets that have punishing conditions in their upper atmospheres. We see lots of planets that are not habitable. We also see lots of planets where we have no idea. It's really important to note that when we look at a press release about an Earth-like planet, what they're saying is that either the mass of the planet is close to the Earth's mass, or that the radius of the planet, its size, is close to the Earth's radius. And they might even be lucky and be able to say something like the surface temperature of the planet, based on a few assumptions, is somewhere in the range between 0 and 100 degrees Celsius. Now, a lot of these stories you hear, all we know about these planets is either their mass or their radius. We actually don't know much about their atmospheric composition. It's really hard to figure out what their composition is. We can do it reasonably well for more giant planets. It's taking a lot of effort to push that technique down the size scale into something that we would regard as a terrestrial planet. So the word habitable gets used a lot. I don't think we should, because a lot of the time when people say habitable, what they mean is warm. They mean it's in the right temperature range. But really, habitability is a very complex concept, and it's not just about temperature. It's about the water availability, the pH of the water, its activity, what electrons are floating in there, what's the chemical mix, what's the magnetic field. And this is one that we know about as a problem for astrobiology, but we find very hard to probe for exoplanets. It's really unclear how we'll ever find out how a terrestrial planet has a magnetic field at all. And if it doesn't, then that planet is missing an important shield against very harmful stellar radiation. And the techniques we have tend to point our focus towards planets going closer to the star, so planets going around smaller stars, but orbiting closer so the temperature remains clement, quote unquote. If these planets don't have a magnetic field, then there's no chance these things have any life on them whatsoever.
Now, this leads to something that's been in the literature has been popping up a lot lately, this idea of detecting biosignatures by characterizing exoplanets as we get better equipment, like the James Webb Space Telescope, whenever that finally happens. Do you think that the landscape's going to change and that we will be able to tell more about these exoplanets as time goes on, or is it just probably not going to ever be on the table for us to detect life at a distance?
Well, I think the biggest sort of trope in this area is that, an astronomer's going to be looking at a spectrograph or at an observation, and they're going to see a characteristic line and they're going to go, Eureka, I've detected life. What's probably going to happen is they're going to see some lines in the spectrum and go, that's interesting, and write a paper saying, look what I found, isn't it interesting? And there's going to be a slow build of evidence, and it will take quite a bit of time. I don't think you'll be able to confirm with one observation or even a handful of observations if a planet is inhabited. It will take decades. And I think one thing that we're going to have to be careful about is how to keep the public engaged with a story that takes a long, long time to reach its end. And what's going to be quite difficult is that we're going to see this story progress from, that's interesting, to, oh, actually, it's a false positive. That thing we saw, which we thought was signs of life, is actually geological activity. We may even have the more frustrating opposite thing, which is the false negative, where we look at something and say, that signature is probably not biological, but with later observations, many years in the future, we can go back and say, oh no, that was biology. We just didn't see it properly. So I think the idea that most of the public have in their head as how this is going to work isn't what's going to be the reality. There's not going to be a eureka moment. There's going to be a moment where the probability of this planet being inhabited goes up a little notch, and then more observations happen and it goes up another little notch, and then more observations happen and this goes up another little notch, and it'll be a slow, agonizing climb up this ladder of probability from a few percent to 70 to 80%. And we might not get much higher than that. And at that point, all we can say is we're 80% sure this thing is inhabited. That might be good enough for some people. It might not be good enough for other people. Some people might just say, well, look, you can't say that. You can't say it's 80% inhabited, or you can't say it's 80% sure. You've got to be very sure. You've got to be, 99% sure, which is, something more approaching the scientific standard for sure. When we detect the Higgs boson, for example, it's not 80% certain we detect it. It's 99.9999999% we detect it, right? I think we might struggle to get to that level of absolute certainty for life on other planets, especially if they're outside the solar system.
That leads to, that's somewhat of a problem for a lot of areas within astrobiology is the ambiguity of something. Just because you see oxygen and methane in an exoplanet atmosphere does not necessarily mean there's a biosphere down there.
No.
It could be created by different mechanisms. And it leads to, I think you're right, in that as we explore this stuff, it's going to be really ambiguous, the biosignatures. With a few exceptions, I mean, if somebody sees what's clearly a vegetative red edge, or one of those types of biosignatures, maybe it might be different. But this is also a problem with SETI too, because I think the public thinks that you're going to detect a signal with a message in it. And no, that's probably not going to be what happens. It'll probably be somebody's radar or some communications internal to them that we can't ever decode. Do you expect that we'll ever have an unambiguous answer or have any kind of information about an alien civilization itself looking through SETI, or will we just forever say radar?
Well, to go back to your point about the red edge, there are false positives for that as well, which is kind of sad. There are false positives for everything. So looking for a technosignature, looking for a sign of technology, is a slightly surer bet, because technology does things that natural things don't. So if we were looking for a signal, and even if the signal doesn't contain information, the nature of the signal itself will tell us something about who is sending it, whether it's being sent by, a spinning neutron star, or being sent by a radar system, or being sent by a transmitter. So yes, the public are probably slightly disabused of the notion that we'll get a signal and it'll contain the prime numbers like it did in Contact or something like that. The chances are that what we will see will be something like static. If you're encoding your information in the most optimized and efficient way possible, and the person on the other side doesn't have your encoding system, it will sound like static. Okay, that's a fundamental theory of information theory. So it may well be the case that we see something, it looks like static, but the fact that it's being transmitted on a very specific set of frequencies and that it's very powerful might give us some indications. If it's coming from a planet, then that planet's going to move around its star, and so we're going to see the Doppler shift of the signal as the planet moves around the star. That might be a good indication that it's coming from a planetary body. That might give us some hope that we can understand that. But after that, we start to struggle. We've got to be careful that what we're looking at isn't being generated by the Earth and being bounced off something else, which is almost always the case when SETI searchers find something. They find a signal and go, that's very narrow in frequency and it's very strong. And they find it's a signal that's come off the moon, or it's come off a satellite or something. And it's actually a terrestrial signal, it's one of ours. So there are limits to what you can do. On the other hand, if you're looking for an atmospheric technosignature, so you're looking at an exoplanet and you look at its atmosphere and you see certain lines in its atmosphere, you may have that eureka moment, because technology can produce things in the atmosphere that nothing else can.
Most notably CFCs, as I recall.
Right. So if you see something like a CFC in the atmosphere, that's produced in factories, right? So if you see CFCs, you see factories. And if you see factories, something has to build those factories. So there is some form of intelligence building those factories. And it seems to be the case that if we use the James Webb and we picked some very odd-looking stars, so we picked a white dwarf, which is basically a dead star, and we found a planet going around it, then the nature of the white star spectrum, the white dwarf spectrum, is such that we'd be able to detect the CFCs in that planet's atmosphere, and that would be conclusive proof that there's a dirty species over there. So there are signatures like that. There are some other signatures that might give us some indication that there was a civilization there. So a few years ago, some colleagues of mine, we got together and we wrote a paper about this and looked for the ways that we could see dead civilizations. And some of the things that we thought about in how civilizations could kill themselves leave quite specific spectral signatures. And if we're lucky and we're looking at the right time, we could see signs of that in their atmospheres, and that would be proof again that something lived, but it would also say that something died.
I remember that paper. That also had in it, as I recall, rotting vegetation producing unnatural amounts of, what was it, methane?
It was a methane byproduct. So there are certain byproducts of rotting vegetation that just don't exist, even in your standard geochemistry. And they're quite strong. They've got quite nice strong lines, and they persist for quite a while. So if there was some kind of pandemic virus that killed all life on this planet, there would be an interval where if you were an alien looking at the Earth, you'd see this huge spike in this particular line. And that line would tell you, okay, there's a lot of rotten dead stuff there. So it's grim, but that would be one way we could see, yeah, that has signs of life.
So it might actually be a signature of mass extinction. So if you're having, like one of Earth's past mass extinctions, maybe you might see the effects of it in the atmosphere, perhaps.
Mass extinctions are harder because they take a bit too long. Natural mass extinctions take quite a few million years to run their course, and so the die-off is slow. If it's human-caused, we're doing it a hell of a lot quicker. So yeah, that's potentially possible. I mean, to make the signal strong, you want to basically kill everything within a year. And to do that requires like a calamity. It requires something pretty serious.
Could an asteroid pull it off? A sufficiently damaging asteroid impact? Or would you just not see it at all? I mean, because of the atmospheric effects of the asteroid itself.
I think you'd be missing it from the fact that the asteroid itself would just cause a nuclear winter and produce huge amounts of obscuring dust. So you'd be hard-pressed to say that was a living planet hit by an asteroid as opposed to that was just a planet hit by an asteroid. And to some degree, that's the same kind of effect you would see if we activated all our nuclear weapons at once, which is another way we could get rid of ourselves. It would look a bit like a weak asteroid impact. A lot of the same features would be there. The radiation byproducts wouldn't really give us much to see. So again, there are certain things that are signs of potentially dead life or stupid life, if you like. But these can also be confused with fairly natural phenomena that can produce, huge amounts of energy when they smack things pretty hard.
So would it be possible, let me ask you this, because I know that nuclear weapons have characteristic double flash emissions and things like that. Could you detect that at a distance if you just happen to be looking at a planet when it was undergoing a nuclear war? Could you detect that, or would it simply not it wouldn't make it?
So we tried to calculate that, and it seems to be the case that even if we detonate everything at once in the same location, and we're beaming the radiation in a certain direction, it'd be tough to get that outside the solar system. You'd have to be probably within the orbit of Saturn to see it. I think that was the calculation we came to in the end. So the double flash thing is good if you're in low Earth orbit. It's a great way of detecting nuclear explosions, but it doesn't travel far enough. It's just not strong enough.
Yeah, as I recall, the Vela satellites back in the 1970s did specifically that, to just search for nuclear testing through the double flash. Now, one last thing I wanted to ask you about this. If you're looking at a civilization that has destroyed itself, might that imply that one of the other solutions of the Fermi Paradox is correct, and that civilizations simply almost always destroy themselves, and that the rule is that technology is always deadly to a civilization? Do you think there's any validity to that?
Well, I think this is partly what I'm leaning towards, is the fact that when you look at biospheres without intelligent life in them, the biospheres maintain a certain level of balance. Okay, natural disasters can disturb that balance, but it will restore that balance eventually over time. It might take millions of years. When you look at biospheres where you introduce intelligence, there's a huge instability in the environment, mainly because that intelligent species is destroying its resources. When we talk about things like climate change, and there's a lot of discussion here in the UK about the right words to use, whether it's climate change or climate breakdown or whatever you want to call it, I call it human habitat destruction, because that's what it is. We're destroying the habitat, but rather than just destroying the habitat of animals, we're destroying our own habitat. And so it leads me to think that maybe intelligent life finds it very hard not to destroy its own habitat, because that's not its end goal, if you like. Its end goal is to produce as many copies of itself as possible. And the way it can do so, the way it can cheat the biosphere, we can use technology to clothe ourselves, to feed ourselves, to propagate ourselves in ways that nature, quote unquote, never intended. I wonder if that's a common trait, and that whether it's a very specific disaster like a war, or just the fact that we don't really have the wisdom to be stewards of our own environment, it may just be that intelligent life is short-lived. And that was one of the reasons we went looking for signs in this paper, was this idea that, well, if that's the reason we don't see anything out there, how do we test that theory? And the way we test it is we look for the dead. And if we can find ways of looking for the dead and we find them, that tells us something about our existence in the universe, i.e. we're not alone. There was at least one other civilization, and there was us. The other thing it tells us is a rough guess, a very first estimate on the shelf life of humans. What's the future of our species? It might also give us the wisdom we need to maybe avoid some of these obstacles. If we can see other civilizations dying of climate change, or dying of nanotechnology, or of genetic engineering, or of the grey goo, nuclear war, the list is huge. If we can see these things happening out there in the universe, can we learn from their mistakes?
That would be probably the most valuable thing that could ever come from learning if intelligent life actually exists, is to see what ended it, as opposed to something far more scary, like, you're looking out and you see a machine civilization or something that is indifferent entirely to you, but it's just so all-powerful that they're, it's building Dyson swarms around stars and everything else, that you could have no defense against it if you ever got its attention. Which brings into the question, what are your feelings on if we got some sort of a message, a communication, or we saw a beacon, something that's just blasting out narrowband emissions at 1420 megahertz and doing it in a way that has to be of alien origin? Should we contact them? Should we do anything proactive, or should we just quietly watch? What do you think is the safest or smartest thing to do?
Well, I know the community is extremely split on this, and that I think you've had guests on your show that are very much, hi, let's talk. I'm very much in the let's keep quiet category. I think we have a lot of growing up to do as a species. I look at humanity as a bit of a teenager that doesn't know how to clean its room. Is it really time that we go to the bar and socialize with the rest of the universe? I don't think so. I think we've got some work to do. I think it's important that we listen, that we watch, and that we pay attention. But I don't think we're in the right place to actually start shouting at the universe. And ultimately, if there are other civilizations out there and they're looking at the Earth, there's a good chance that if they look at us, they'll see a very interesting picture, and they'll see lots of biosignatures together in the same place. And that tells us, if you see one biosignature, you might think, oh, that's just geology. If you see 6, then you start to build a picture of where that comes from and the chemical reactions and the cycles. And when you do that and you come to the conclusion, oh, this is biology, that's chlorophyll, that's photosynthesis going on down there, that's signs of active ocean life down there. Yeah, okay, I'm starting to build a picture. This planet is inhabited. And if you really stare at us with your most powerful telescopes and you're not too far away, you might start to see our radar chatter. You might start seeing some of our TV emissions, although they're pretty weak. There's a good chance they see us anyway, right? If they can tell that we're here and they're that advanced and they're not miles and miles away, if they're within, 200 light years, right? Which is next door, galactically speaking, but if they're within 200 light years, they can see us. You'd better hope that they're not. I think that's my answer.
Yeah, absolutely. Absolutely. And we have to take another break. I'm joined today by Dr. Duncan Forgan, author of Solving Fermi's Paradox. Back in a moment. And we're back. Now, Doctor, we were talking about something interesting, that civilizations could destroy themselves, and they may have a very short shelf life. We've only had civilization for a very short time in the geological sense. Wouldn't that also be a solution that, you just don't ever exist at the same time as another civilization in order to detect them directly? So if you look for dead civilizations, or even this idea of exoarcheology, looking for essentially aliens, remnants, how likely do you think it is that would be detectable within, say, 20 years? Do you think we're going to have the instrumentation to really start looking at that, or is it just something for the future?
So the work that we did in looking for the dead civilizations, we focused on the recently dead. We looked at the first century after, whatever cataclysm had befallen them. And the signals that we were looking at didn't last much longer than a few decades, and some lasted only a couple of years. So detecting the recently deceased is going to be hard, because as you say, you've got to be looking at the right place at the right time, given the fact that your two civilizations may be separated by a great distance and that the light takes some time to travel. So, you've got to be quite lucky. In terms of archaeology, unless they're building very big structures, it's quite hard to accept that we can see buildings on other planets. And if they're ruins or if they're half buried, that makes it even harder. If they're building large structures in space, potentially a lot easier. If they're building, Dyson sphere shapes or partial Dyson spheres or anything like that, then that obviously has effects on how the star looks to us. And these are things we're very good at spotting. So the techniques we use for detecting exoplanets, we could easily use for that. And in fact, it's a bit of SETI we get for free, effectively. Whenever we do a study for exoplanets, we're doing a quick piece of SETI as well to kind of cover out the more, crazy ideas that maybe there's a giant space structure there. And if it was there, we would see it. So my feeling is that the signatures that we were looking for on the planet, if you're thinking about on planet, it's not for the current generation of technology. It's probably not for the next generation like James Webb. It may not even be for the generation after that, which is the successor to James Webb, Loeb. Yeah, it could be sometime in the future. It's not clear to me whether we would see things in the next 30 years. It may well even be longer than that.
Now, say something is found. A lot of people are going to say, well, the government's never going to tell us about it if they do find it, which is silly because it's not up to the government. But what are the protocols? What happens when a detection is made? What steps happen after that? What are the scientists going to do?
So the protocols that follow detection, and these protocols are assuming you're seeing like a radio signal or an astronomical signal. Essentially, the first thing you have to do is check you're working. Go and try and see it again. Generally speaking, if you can't see a signal twice, it's not worth talking about. And if you can confirm that it's not, a case of human error, it's not an instrumentation problem, it's a real thing, you go and speak to your colleagues somewhere else and say, I've seen this thing, can you point your telescope at this point in the sky and check? And if they confirm that, then you ask more people and they go and check. And as you build up confidence this thing is real, you then have to go and inform various individuals of your discovery. You should inform the UN, Secretary General. The chair of the Committee on the Peaceful Use of Outer Space, I think, also gets informed. And your nation state needs to be informed as well. Clearly, at that point, you should tell the government that you've got something interesting. The final stage, I think, once all that is done, is that you then announce it to the public. Now, this is kind of laughable when you talk about it now, because these protocols were written in the late 80s and then were revised partially in the early 2000s, but they are very much a pre-social media set of protocols. There's an assumption you can keep a secret for what would be like 6 months. Nope, that doesn't happen anymore. It's quite clear that if any major scientific discovery is made, it's on Twitter the next day. So, the example I give is the first detection of gravitational waves by LIGO. I was aware of that happening maybe 6 to 9 months before the press release. And I'm not involved in any of these collaborations, right? I just know the right people on Twitter. And if you just read between the lines of a certain tweet, then it's revealed as a secret, right? So, even in large collaborations where there's a very strong onus on keeping things tight and hushed up before you go public, before you confirm the thing, it's going to get out. So some work that I've been doing the last couple of years is addressing this and thinking about how we should go about changing these protocols to be a bit more 21st century and to acknowledge the reality that, the internet exists. Right, which is a very good means of telling things and telling stories, but also telling misinformation, telling fake news, telling lies, spreading propaganda. And if there's anything that will be a conduit for this, it is this kind of activity. So it's really important we figure out what to do, and it's important we protect the people involved, because if you're a scientist who discovers intelligent life and there are people out there who cannot cope with the fact that intelligent life exists and they get your information off the internet, then what are they going to do? The security of your person and your family could be threatened, and we should think carefully about this. It may never happen. I personally don't think we're going to see any signs of intelligent life. I'm a bit of a pessimist. I still think we should search because it's a good thing to do. Even if you don't think you see the thing, you should test it. You shouldn't be an armchair philosopher. You should go out and do the experiment. You should go and observe. But the fact that even though it's a low probability event, if I'm wrong, and if we do find something, the consequences could either be catastrophic, they could be amazing, or they could be People could just be like, oh, what's the next story? They could be, absorbed with politics. I know that my country is certainly very absorbed with politics at the minute. So yeah, it could well be the case that this discovery that you and I would regard as epoch-making is a damp squib in the news. Okay, it might not be. It might be very important. It might be a very big deal. And so we should think carefully about how to protect the people who are responsible for that story, how we protect the story itself, and how we make sure that whatever we do discover is put to the good of all people on the earth.
And the advancement of science. Now, I'm sort of in the same boat in that I don't expect to see evidence of an alien civilization within my lifetime. But that's not the only chance we have of asking ourselves, answering the question, is life on Earth alone? And that's because we have quite a few ice shell moons in the solar system that have liquid water under the surface, most notably perhaps Europa, and of course Enceladus. Do you think that the chances of there being something, even if it's just microbial, in the oceans of Europa, do you think that's a strong possibility, or do you think it's probably not going to be the case?
I would say I'm somewhere in the middle. I would toss a coin. It doesn't seem ridiculous to me that these moons could be inhabited. The conditions at the deep ocean of these moons is not dissimilar to the conditions in the deep oceans of the Earth. We know that there are certain forms of life that just don't care about the sun and don't need it. As long as they can get energy from somewhere else, that's fine. And Europa and Enceladus have energy sources that come from the tidal forces of Jupiter. So yeah, that might well be it. I'm fairly ambivalent. I think it's quite possible, but I'm an astronomer first and a biologist second. I'm probably not even a biologist at all. So I'm not sure. I think it's quite possible. I'm not sure if I would go on and say it's likely or unlikely, but it's a very exciting prospect, because if that's true, then there are presumably quite a lot of icy moons, not just in the solar system, but in all sorts of planetary systems. And if that's the case, then it could be that life on warm, wet planets is actually the rare thing, and that what's most common in the universe is microbial or even larger forms of life and in these subsurface oceans.
It is somewhat mind-boggling if you think about it, because we seem to find the possibility of subsurface liquid water in quite a few moons in the solar system, and even an asteroid Ceres may have a slushy ocean of some sort. And if we found microbial life at any one of these, and it's genetically distinct from Earth life and didn't, hitch a ride there, or vice versa, then the universe probably teems with microbes with these ice shell moons, because they're probably everywhere. They're probably ubiquitous in star systems. And that changes the equation too, because if everybody's worried about certain stars being never suitable for life because their habitable zones are too close in, like the red dwarfs. Well, what about an ice shell moon around, a planet rotating around a red dwarf? Could life still show up there because it's shielded by the ice? So I would find that to be a really alluring concept, that the universe is alive. It's just microbial, and that we're rare, but microbes aren't.
Yeah, and I think for me, what this would do, if we could even prove that one of the moons of the solar system was inhabited, is that we could finally stop calling the habitable zone, because to me, I don't think that's a good description. What you're asking when you say the habitable zone is, if you take an Earth, like an exact copy of the Earth, right down to its moon and its magnetic field, and its atmospheric mix, which is quite specific, and it's only really arrived presently, the atmospheric mix of the Earth compared to what it was billions of years ago is very different. And that's another factor in climate change, is that even a few 100 million years ago, the atmospheric mix was different. You take this planet, which looks exactly like ours today, and you move it around at different radii, different orbital radii, and you get different temperatures, and this is how you build up your zone. All that's telling you is where Earths are suitable for life that lives on the surface. It doesn't tell you anything about where you should put your icy moons. So the habitable zone, if you like, the true habitable zone where any form of life can live on any body, could be much, much bigger. And we should therefore call this thing we call the habitable zone the liquid water zone, or the warm terrestrial zone, or something like that, which is more descriptive, and acknowledges the fact that maybe life is much richer and more interesting and amazing even than it is on the Earth, which is already pretty rich, interesting, and amazing to begin with.
Well, Earth's life is resilient, and if the rest of life in the universe is resilient, it could surprise us. Which then you get into really speculative stuff like Dyson sunflowers and things like that, who knows. Now, this isn't the only way that we can solve that question or get close to solving that question. There's also the biochemists doing the follow-ups and successor experiments to the Miller-Urey experiment, where they're trying to see how hard it is to get life started chemically. And if they ever nail that, we can say, well, that's really hard and probably doesn't happen very often. Or we can say, man, that's probably happens a lot. But then you have to get through the filters, the great filters. What do you think is the biggest showstopper for life as you go through the filters?
They're all pretty big, aren't they? Just getting yourself set up to be self-replicating in the first place is hard. Having proper inheritance of genetic information is hard. There are a lot of things about us that seem to have happened by accident, that our cell structure seems to be the consequence of two organisms colliding and one being eaten by the other and then realizing, hey, this is actually a good setup, let's do this. Is that always destined to happen? Probably not. I think, to be honest, if you're taking what we see currently as evidence there's nobody else like us, then what that means is that the great filter is somewhere in our past. Okay, we somehow managed to survive that particular obstacle. And if that's the case, then I would put it much further back than humans. I think it probably goes back to the development of brains themselves, the idea of having a nervous system like ours that's sufficiently complex and advanced that at a certain point, you have this thing that happens that I think it's 70,000 years ago or something, where you take our ancestors who have anatomically quite similar brains to us, but we're not capable of doing the things that we're doing, and then suddenly everything changes. You have, the first indications that we have a real society, we have language, we have inheritance, we have rapid evolution of tools and technology and culture. So, yeah, I would say it's probably to do with the formation of brains, because you can be quite a successful organism without having a brain. You can have your nervous system being quite distributed to the point that you don't need a central nervous organ like we have. Yeah, I would probably put it there. I think that's where I would end up.
Now that leads to a possibility that intelligence could be so rare, and for all intents and purposes, at least within the local group of galaxies, unique, that would make Earth very, very special. Mm-hmm. And that we actually are the lottery winners of the universe, so to speak, or at least are part of the observable universe. So do you think that that's more likely than life being somewhat ubiquitous? Do you think it's more likely that we're just living on a very, very special world?
Well, I think it's immediately clear, whatever you think about intelligent life or life in the universe, we are living on a very special world. I think that's one of the great things about astronomy, is it gives you that perspective, allows you to look back and say, the Earth is amazing. And I think your scenario of us being alone in the local group, it could be possible. I mean, it might well be the case that we're not actually alone, but in terms of the distances that it would take us to traverse to get to the next civilization, or for a radio signal to get there, we're effectively alone. We can never communicate. That might be true. And if it is true, and we are the lottery winners in our part of the universe, how are we spending our winnings? And I think that's the thing that depresses me. So this work kind of lifts me up, and it also brings me down. It lifts me up because it makes me think of, just how amazing this planet is and how lucky we are to be here. But it does bring me down when I think what we're doing with that incredible fortune. I think I tend to lean towards the idea that maybe we're not entirely alone, but it just is the case that we pass like ships in the night, never knowing that we exist. And that maybe it is the case that there's not many of us. Intelligent life is rare, but not too rare, but it's short. So I tend to take a little bit out of column A and a little bit out of column B. That maybe there's hundreds or thousands of intelligent civilizations out there, but they tend to live and die without ever relearning of each other's existence, just because their existence is so short and the galaxy is such a big place.
It just goes to show that we really need to pay attention to preserving the planet and preserving our own civilization and intelligence, because it's precious. If it's so rare and it's precious, then it becomes an imperative for us to survive.
And I think that's one reason to do the search and then not find anything. Some people come to me and say, if you don't believe you're going to find anything, why bother? And I think, well, if you can confirm to a fairly high level of certainty that there are no radio signals, no artificial structures, no signs of any technology in 1,000 light years of the Earth. What does that mean for us? How should we look at ourselves as a species? If we can take that result and we can kind of feed it into the human psyche and say, look at how special you are, and look what you're doing to yourself, maybe that might help us snap out of some of our worst impulses and might help safeguard the future of our families and our future of our planet, basically.
That's interesting. So in such a case, then a null result from SETI is still a net positive for the human species.
Yeah.
And it just shows us that we're rare.
Yeah, it doesn't matter if you don't find anything. The important thing is that we looked and we saw what it was to be human.
Absolutely. And on that note, we are out of time. Thanks for joining us today, Doctor.
Thank you for having me.
Well, that was a good show. Let's see what I missed.
You have one new message.
Prompt service is required.
End of messages.
What? Why is Schrodinger's possum taunting me on my answering machine?
I don't know, John, but he sounds angry.
I just want my LeBaron back.
It has gone on to better things, John.
I guess I'll have to start looking for something new to get me around. I do need my McRib. Damn it!
John, remind me to analyse your diet.
Wait, stop it! I like the spray bottle better.
That's a good idea.
Ah! Water and electricity don't mix.
On the contrary, they mix rather well.